going to talk about section 9, which is basically distributions, statistical distributions. And this one, I kind of want to give you guys just an overall feel for it and like go through those parts because they're distributions. Note that we're not going to talk about all of them. The curriculum does have a lot. They have a few other distributions that we're not mentioned, but I'm going to show you some main ones and going from there. And statistical distributions are really useful in the sense that knowing how to create those distributions from probability and randomness will allow us, when we see those distributions again, we can actually take those value or take these distributions and apply certain tests or other, we can reason what's supposed to be. So this will be useful for when you get to our module project where you are going to explore the data and actually see, okay, well, like how is this distributed, you know, and all that stuff. So I'm going to go and start sharing my screen. And this will actually be a continuation from last time. So if you guys remember, we started a little bit for a second. Sorry, see, I lost you guys now. We started on talking about randomness. And so I mentioned a little bit about like, you know, what random numbers are, how computer kind of, like how the fact that computer kind of generates random numbers is not really random, but we say it's close enough, which is important when we're making our distributions and stuff like that from simulation. And I also showed you guys an overview of a sample distribution. One is actually from a test data set. In this case, it's a CSV file, California housing testing. Basically, it's just some information. And we specifically looked at the housing median age and we plotted that out. Basically, just how frequently does that come up? And you can see here the frequency of each of those values, the different ages of the house. And I plotted out here the mean and the median, or sorry, I plotted out the mean, the average, and then also one standard deviation away. So in those green bars represent one standard deviation up and one standard deviation below. And we also have this blue line here, which we'll talk about today, which is basically a certain kind of fit, basically trying to extend it to more continuous, because right now it's discrete. So this allows us to say, well, what would be the distribution, or what would the distribution look like if it was like, for example, instead of 10, the age of 10, maybe it's like 10.5 years. And so that's the idea of using a continuous distribution like this, okay? So again, that's just what we had from before. I also created a normal distribution, which we'll see a lot of. And basically this creates a random set of 5,000 different data points that are randomly distributed, but in a normal way, with a certain standard deviation of 2.8. and average mu, that's what you should go call it, or average of 14. And you can see here, I plotted that out. And you can see that's where 14 is as a standard deviation, even though these are randomly created, okay? So that was what I showed you guys last time. Let's dive into statistical distributions for today. So the first thing, so if you guys have started up at the, section 9 now, you probably have seen some of these things: probability mass function, cumulative distribution functions, CDFs, PDFs, PMFs. So we're kind of work our way through. And so the first thing is going to be PMFs. And basically a PMF is, you can almost think of it just like a histogram, okay? Except we scale it down in a certain way. So a probability mass function, PMF, the reason why it's called masses is that it's basically, it shows how much of this thing. And that's why it's like, I think the analogy is like there's masses on a bar, and that kind of makes you figure out like how things are distributed out. I think that's why in general we tend to call it a probability mass function, but really the mass just represents how much stuff, and that's what we mean by mass, okay? So I think this is actually taken directly from the curriculum here. It's also called a stem plot, basically, because they all look like little stems coming up. And you can see here is that we see how much each thing extends outward. And you can see it looks very similar to a histogram. If I just made this into a bar, you probably wouldn't like blink twice on saying that's a histogram. The main difference though, you'll notice, is that on a PMF, in this case, we actually have it scaled to what the curriculum calls normalize. These values don't represent how often they occur, but instead represent the frequency, or not the frequency, sorry, the probability of that happening. So essentially what happens, and we'll see this in a second, our coding example, we essentially take a histogram or something that's equivalent to a histogram, and instead of having like, oh, it occurs 6 times, 10 times, 12 times, 4 times, we shrink it down and say, well, we're going to divide by the total number of events. And that gives us essentially a probability, which allows us then to actually add up each part, and we'll get will add up to 1, it'll sum up to 1. So one thing I kind of want to put in your mind is when you hear normal, in a lot of math terms, you should think of the number 1. Basically, when we talk about something being normal, we're really talking about it being the number 1, okay? So I'm going to show you guys a quick coding example. Any questions so far for PMF? And you might notice I'm going to talk a little bit faster today, just kind of so we can make sure we get through this stuff, and I want to make sure. But if you guys have any questions, make sure you stop me. Okay. So right here I have a little coding example of basically a couple dice. So in this case, you can see here I had 1 dice to roll, 2 dice to roll, and right now I'm just randomly picking an integer between 1 and 7, and I'm going to do it in this case 3,000 times. So I'm going to roll 3,000 dice, I'll get like 1, you know, maybe I get 4 sometimes, maybe I'll get 6, and so on. And then I'll roll a second pair of dice, okay? And so I'm actually going to split this cell so it's a little easier for us to see. And I'm going to just print out what they look like so you can see how many values we have. And in this case, we didn't show the whole thing because there's so many values. But you can see, for example, I have 3, 2, 1. That's all the different 1 die rolls. And then I have my second die here, all the different 2 die, the second die roll. And then I also, if you caught this, I actually did a sum of dice where basically you can imagine take the very first one, 3 and 2, and add them together. And then the next one will be 2 and 2, and add those together. So the idea here is that maybe I roll both dice at the same time. I kind of separated it out, but that's the concept here. So now we actually can do some plotting and check out what they look like. Note that this collections right here is just another, it's an efficient way to do certain data structures within Python. It's not necessarily needed to do these things. It just kind of makes it a little easier, a little cleaner code. This is what the curriculum kind of shows off. But just know that there's nothing too fancy. You could have done the same thing with a dictionary. Basically, you could go through the list of numbers, or the array of numbers, I should say, and basically count how many times does 3 occur, how many times does 1 occur, and so on. Okay, so that's kind of what's going on with this collections.counter. So I'm basically creating these different parts, the counter for this die 1, die 2, and not die 2. Or I'm messing myself up. Die 1, die 2, and then the sum of those 2 dies together. All right. So just to kind of show you what this looks like, you can see here is that the counter, the sum of dice, which was this rolls, you can see that's that first 5, 3 plus 2. That's my 5 right here. 2 plus 2, 4. 1 plus 3, 4. And you can see my counter here, which is what this is right here. All it is basically a dictionary. It's kind of like a dictionary, essentially, of saying, okay, how many 7s occurred? Well, 488 7s occurred in this whole list here. Of how many 6s occurred? 439 occurred, and so on. It basically counts up all the different events that happen. If I had a very small roll of dice, it's possible that a number like maybe 2 never shows up. Maybe I never rolled double 1s. So just kind of know that this is all the possible events, that, or not all the possible events, but all the events that happened in my little simulation here. Okay. So now that we have our thing, we can actually plot it out and see what it looks like. So I'm doing some fancy footwork here, but basically know that this PMF die 1, die 2, I'm basically creating a list comprehension so I can actually get the frequency within this part. So you can see here, I get the counter die 1 dot get, and this dot get basically allows us, like, in case I didn't roll a 1, if I had a small number of rolls, if I didn't roll a 1 and I tried getting a 1, see, hey, how many 1s are there? It would give me an error in dictionary. So this allows me to say, well, if it's not there, just return 0. So like, so if I try rolling a 13, 13 never exists, I'll actually say, oh, okay, just there weren't any 13s, give me a 0. And so 0 divided by the total number of possibilities. And this gives me basically that frequency on that part. So sorry, I'm gonna turn off my notifications. I don't know if you guys can see that, but okay. So I'll go ahead and run this guy. Okay, so now I have these different list comprehensions for each of the die 2, and then the sum of those dies. Okay, so now I'm going to split this up so you guys can see this good. And so I'm going to show the first die, and this right here, you can see I did, in this case, the plot, I ranged it from 1 to 13, basically so I can see the full spectrum when we get into the sum of dies. And this makes sense. We have 1, 2, 3, 4, 5, 6. Those are all the possibilities for one die, right? And our die 2 is a different, I rolled that 3,000 times, but you can see that it's not quite the same distribution. You can see here is about 17% of the time I got a 1, but then a little bit lower, maybe like 16%. I rolled a 2, and you can see here it's much more even along this line. In fact, I didn't get that many 6s here. And that's just probability, right? It's not something that would necessarily happen every single time. But you can see in general, they're about equal. And if I could roll it more and more, they'd approach closer and closer to actually being equal because it's a fair die, all right? So you can see this part. And of course, we didn't get any of these values for 7, 8, 9, 10, 11, 12, right? Because they didn't, you can't roll a 12 with a single die. So now we can actually do this addition and say, okay, what if we added each part? So we rolled, the first one I rolled a 3, the second one I rolled like a 2. We add those together, I get a 5. Let's see how many times that happens. So any predictions on what this will look like? And I think you guys might have an idea of, first of all, it's going to be from 1 through 12. Are they going to be evenly distributed? Okay, I see some head shakes, good. So yeah, it won't be evenly distributed because you probably have played dice before, is that getting doubles, for example, is a lot, like, I'm sorry, not getting doubles, but getting like a 2, there's only one way to do a 2, right? Versus like a 7, there's many different ways for you to get a 7, 3 and 4, 6 and 1, you guys get the point, okay? So you'll see that there's gonna be a lot less on those other parts. And you can see here, not bad, right? We can see like, 1 is obviously impossible. We can't roll a 1 with 2 dice. 2's relatively infrequent. 12 should be also just as infrequent, but just know that's a little bit different. So we rolled slightly fewer double 6s than we did double 1s. And that kind of makes sense too. I mean, we can't directly cause this, but you can see, oh, there were fewer rolls of 6s than to 1s. So it kind of makes sense that you would probably have that, but that didn't have to be the case, right? But now we can see here, we get this this distribution here, and we can see that 7 is the most common one, with 6 being second most common. And if you know the numbers of how this would work, you'd say, well, it really should be like 6 and 8 should be closer together, but just by pure chance, we didn't, okay? If I reran the simulation again, we wouldn't have the same values. And so right here, we have the same idea here, but instead we have a histogram. And so this histogram, if you look at it, it's the number of counts. So we can see we had almost 500 of the 7s, and then we had something like around like 450 of like 6s. So you can see that this right here is the normalized distribution, this PMF, right? And this is our classical histogram. Usually it's called the frequency, saying like how many times this happened. And all we did basically was divide by the total number of occurrences, and we shrunk that guy down. So that's actually all that's going on here. All right. So any questions on this thing? No?
How come the histogram looks a little fat between?
I think I messed up on here. My guess is that I did this part incorrectly. Let's see. There we go. That's much better. Something's not quite right still. I'm trying to think what's going on. But yeah, it's something to do with my range, with how I structured it. It's probably because this really should be 2 to 13. And so the problem is, I think someone had this issue before, is that this range right here is going to tell you how many bins to have, basically going from the start to the end. And depending how you structure it, it's going to say how many bins. So I think if I did this right, I'd want 12 bins, no, 11 bins, right? So I believe that's what I actually want, and that would be structured correctly. And if I wanted to match with this one, it really should be from 1 to 13. Is that right? There we go. Something along those lines. I want to make sure. I'm kind of doing this on the fly right now, so. But just know that like this right here, I think someone mentioned that. Oh, I think it's Giovanni who mentioned it in the Slack. Yeah. And basically, when you do this histogram right here, note that these will tell you the end of your bins. So this one should describe where the first one starts, and this 13 should describe where the last one ends. So you just have to make sure you have that correctly, and then the number of bins, it'll try to automatically figure that out. So again, you have to kind of be aware. So sometimes you might get some funky stuff, like, wait, that doesn't quite make sense. Always double check. And of course, you can check out the documentation, from a quick reference here, or you can, of course, I suggest looking up, usually it's easy just to Google it, but you can just do the question mark and then the thing you're looking for, or help and that stuff, okay? But the main thing to know is that these are really the same thing. They're just scaled down, okay? Because, or this one is scaled down from this one, because we basically made it into a probability of how often this happens. So if you added up all these numbers, they should add up to 1. It's normalized. Okay, cool. Any questions on PMFs then? My probability mass function. Okay, and you can think of PMF as like discrete. It's like there's not like a continuum. Like you notice like there's only, this is why we actually tend to do stem plots like this, is because you can only get 3. You can't get a 2.5. That's not a thing that you can do. So that's why we don't have anything here. Histograms is a little less clear when you write it like this, because obviously the histogram's like, well, that's binning it within that. So if there was a 2 to 2.5 to 3, it would bin it all within that one bin. So that's why we make it really clear with the stem plot. Okay, so this leads us into cumulative distribution functions. And so our CDFs are similar in the sense that like they're also describing the same thing. So there's nothing new that we're doing. The difference is though is how we show it. So cumulative basically just means that we're adding up all of them up. So we start off with, like in this case, we'll show you in a second when I do this plot. Well, I'll show you this plot now, and then I can explain from here, is that we still start off with 1 of like, these are our sum of dice, and we go up to 12. And basically we're accounting for all the different events that could possibly happen. So basically you start off like, well, let's just count from like no events. Well, that's obviously 0, nothing that happens. Like, well, how many events happened that were 1? What percentage of events happened that were at least 1? Well, no events again. What about 2? Okay, we have a certain percentage of them. And then we say, okay, at least, or at most 3. And then you say, okay, that means you count the ones that were 1, which is none, a sum of 2, and a sum of 3, and we kind of bump up. So it accumulates, right? That's why we call it a cumulative distribution function. And this actually kind of, if you look at this carefully, you can see that certain steps are much larger, which makes sense. These 5, 6, 7, and 8, they're a much higher rate of happening. So you can see that they go up much higher compared to going from 0 to 2, right? You can see there's a very small step. And same thing for that 12. That 12 is very small. Not that many happen here. You barely go up. But the point here is that you account for all the different event spaces or events that could happen in that event space, and it'll always add up to 1. And so you can start doing things like, you know, first of all, how big those steps are, but also with a very like large number of events, you can see how the CDF increases. So if you see an increase, and I would kind of draw on here to home in my point, is that if you have a CDF that looks more like this is kind of closer, if I had this more continuous, to look like this, versus something that looked closer to like this. Okay, you know that this stuff, the stuff early on in this event space, happens more frequently than the stuff over here. But over here, you can see it increases very quickly. So the events that happen within this space for this red line are more frequent than the tail ends. And so this is just another way to basically show the different distribution. Okay, so if it was instead, if I had a PMF that was like this, where each part was equal, what do you guys, anyone got a guess of what that CDF would look like? So like these should all be like the same number. So rolling a 1, 2, 3, 4, 5 should all be equal. Does anyone have an idea of what that?
Symmetric steps.
Yeah, so we'd have symmetric steps, right? So that's good. So each step up would be the same size. If I was a good drawer, I could do symmetric steps, right? But the whole point is it would be symmetric. And if I had many, many steps, let's say I had like a million different events and they're all equally likely, what would that, it's going to be some kind of like smooth curve. What would that curve look like?
Would it be a straight line?
Be a straight line, good. So because you're always increasing the same amount all the way through. So you would tend to have a straight line like this, okay? And so like if I had this, like, you know, like Giovanna had said about equal steps, I could draw like a straight line right through here if I was a better drawer. And you can kind of see here, if I had more, I might have something that looks like a curve like this. So you can see it kind of curves downward. It's not perfectly straight. There's definitely is some kind of structure to this. And this is where, again, looking at a CDF can help you determine what the different events do versus like looking at just a histogram. Just another option. Okay. All right. So cool for me to move on then? Any questions? All right, awesome. So next we have is our PDFs, and PDFs are probably more common in the sense because it's a probability density function. It basically allows us to look at a continuum versus something like a PMF, which is discrete. So our PMF is a continuous function. So here is basically, you can see this right here would be closer to a PMF, a probability mass function. If I had a stem, that would probably be better. But you can see here, these are really probabilities, right? How basically, they're not, it's not like the number of things, it's just basically how frequently that happens with that small values. And this blue line here is more of the PDF here, basically this continuous version of this. And note that when I do this PDF, it doesn't exactly fit onto this thing. And we'll talk about the different ways you can kind of form these PDFs, all right? So, so you always use a range. Can we find the exact number? So this is where one of those things where it's like, you know, can you ever hit the bullseye? So let me ask you, if I told you, like, you know, I want you to hit this exact spot, does anyone got a guess? Like I said, all right, it doesn't really matter the bullseye. It's like, if I want you to hit this exact little dot, does it, and I throw it randomly, and it can only land on this dartboard, does anyone know what the probability of us finding that exact dot right there?
0.
Ah, good, 0, yeah. So I always say, like, my trick questions are either 0 or 1. And so in this case, it's 0, because basically it comes down to the fact that, like, no matter how accurate you can get, there'll always be like, well, I meant it by like 0.0001 centimeters off to that right. And so you can always put as much precision as you want, mathematically speaking, until basically it's essentially 0. So any given 1 point on a target is essentially a 0 probability. So this is the problem, is that mathematically, that's how it works out. So the problem is if you try to do the probability of this exact number on this, like say exactly 10.12, turns out the probability is always 0. And you're like, well, okay, that doesn't really help me. So when we do a PDF, we actually say, instead of thinking about it as saying, what's the probability of this one exact point, we say, what's the probability of going from basically, like, if I'm using this graph, from here to here, like, what is the probability of getting within this range right here? And equivalent to a bullseye would be like, what's the probability of landing within this circle instead of a specific point? So it's a subtle thing, but kind of know that that's why we're using a range versus a specific point, because we're on a continuum, right? So kind of moving on. Any questions on that? Okay, cool. So kind of moving on to there. We have, so again, normalization. So does anyone have an idea why we normalize the area to 1? Like, why would 1 be such an important number when we normalize? A little hint on here. So one reason why is because then we can translate to probability really easily. Basically, once you know that if this is the whole event space, basically that means that the area underneath there represents the probability, right? So going from, in this case, this example from 12 to 14, we have a probability of saying, oh, 13.6% of the area is underneath there, or the probability of landing within that area is 13.6, or sorry, the probability is 0.136 or 13%, 13.6%. So this is why we actually normalize this, because then we can actually talk about its probability really, really easily. We just say, hey, how much area is underneath the curve? And if you guys remember, like, about how calculus works, we can find basically all of integrals, for example. The whole point of them are essentially to find the area underneath the curve. And so we can actually figure this stuff out. If you took statistics maybe back in high school, maybe, university, you might have had like a book or some chart that told you if you're within this range, what the value is and stuff like that. And basically what it was doing, it was figuring out the area underneath that curve for you. If you recall, not everyone had this, but like you might have had like charts with sine and cosine, and would give you like different values. The idea there is like, well, you could technically figure this out, but it's easier to just have a chart, because they didn't have computers. But thankfully, we have computers that can easily do these kind of things, at least for non-structured functions. Okay. So I'm going to move on to just comparing a PMF, a CDF, and a PDF of all the same data. So you can see here, this is an example of data. It's not mine. I want to make that clear. But basically, this is a histogram of all this different data. I don't know exactly what this data is, but you can see here is that it's all normalized. Actually, I don't believe this is normalized, because you can see this frequency is 1. So you can see frequency here. Usually when we talk about frequency, it means it's not normalized. But you can imagine if we shrunk it down so it does add up to 1, right? But the point here is that we have all these different discrete values, and that's the actual data. That's kind of like all bin together. And then we have this PDF here, which is that black line. That PDF basically is estimating that nice PMF, because the pink is the PMF essentially. And then you can see here in this blue is our CDF, right? Our CDF basically is showing, it's like, oh, it's very common within this area. And then as we get off to the tails, either at the end or at the beginning, there's not much of an increase. And then when we get to the very common stuff, there's a big increase. And then as we get to the end here, there's a small increase, okay? So this is all of them put together just to kind of show you how they relate to each other. All right, any questions on this? Okay, cool. So now that we have to say, okay, we know what a PDF is, how do we make it, right? So the first version basically, well, the very first version, if you wanted to make a continuous function out of this, and I'm gonna scroll up to the top because this one's a little easier. If I wanted to make a function out of this PMF, the simplest way to do it, is anyone got to guess what the most simplest way to make a continuous function using the PMF? Okay, yeah, it's right. It's almost too simple. The way you would do it is basically you would connect points. So you go from here to here, here to here, here to here, here to here, just basically to each point. And that would be your PDF, which you can tell right away, that's pretty crude, right? That's, if I kind of scroll down a little bit so you can kind of see what this looks like, that's a pretty crude PDF, right? It's like, well, technically it hits all those values, it fits on there, but you know, we can tell, like, does it really make sense for it to be there? We'd like to have a nice smooth function, especially when we do, when we calculate things like areas, it's nice to have a nice smooth function to be able to extrapolate from. So the other option is we figure out saying, hey, what does this thing look like? And this is what a parametric fit is. Basically saying, when we have a parametric fit, we say, well, this looks like this kind of distribution, and we know how to mathematically create this distribution. We'll see that in normal distribution, but it's like, we know how to make this out of math. So let's say it is this object, and we kind of pull out the values from there. So for example, this curve right here is something called a Gaussian curve, okay? Or you might have heard like a bell curve before, really famous stuff, is that basically there's a mathematical equation that we can write for this bell curve, this Gaussian curve. And we say, okay, if our distribution, you know, it's not quite right, because you can tell it's not exactly, but it's close. It's like, well, if we say it is a bell curve, it is a Gaussian, we know what the math is, and we can immediately pull out information from the math and basically, well, if we know it's a bell curve, then we can say if there are these values. And that's what a parametric fit is, basically saying, we think we know what the distribution looks like, and we're gonna say it's like, for example, a Gaussian. We know how to write a Gaussian and say, all right, then we just basically take out the values from that Gaussian. Okay. A kernel density function tends to be more common for us. And to be honest, it's might be a little hard to wrap your head around exactly what's going on. So I'm kind of explain this a little bit. So in this diagram, you can see that these little lines right here represent the data points. Okay, so certain data points, and don't worry too much about like this part, but you can see like if we bin them together, like this is more like a PMF, more like a histogram to be honest. But if we bin them together, say, well, there's only one of them here. There are like two values here, so that's why it's twice as big. There's only one value that fits in this bin. There's no values that fit in this bin, and then there's one in this bin, and then one in this bin. Okay, so there's our PF there. If we say, okay, let's consider all of these values, and then we say, okay, let's say there's a chance that maybe that it could have been like a little bit off. And so it turns out like we can say, well, let's say it's normally distributed. And you'll see that we'll use normal distributions all the time because it turns out most of life follows a normal distribution. And there's a bunch, it's nice to calculate, it's nice and easy. And so we can actually say, okay, we have this value right here and say, well, let's just say there's a probability, like that's where on average it would have sit. But we have a little tiny Gaussian distribution, this little tiny bell curve. Say, okay, let's center it around, and I'm not great at drawing, right? But you center it around this little point right here. And you say, okay, let's have another Gaussian drawn out right here, okay? And we basically do these Gaussians like you see in this picture right here in the red, is all those different Gaussians. And you say, okay, that's kind of how we all distribute. And they're all centered. If I had, let's say, I do it in blue. If I could like draw a line directly up, you can see that it's centered right here. And like this one, for example, is centered right here. Okay, so basically, in a sense, we kind of smear out the data point Okay, and that's essentially what we're doing, but we're smearing out in a very specific way in a normal curve. And then we say, okay, let's take all those points individually and then add them up together. And so if you've done something like physics, like with wave dynamics, basically that's what we're doing. We're basically adding up the waves. And so you can see that there's a bunch of these little Gaussians together, these little bell curves. And so we add them together so they kind of constructively add up together. And you can see this huge bump right here. That's them being added up together. If there's a little bit, like for example, like there's some curve here, but there's nothing down here, we don't basically, it's like we kind of subtract it off. So you can say, okay, it's not as much available. And then if there's like these tail parts right here that are being added together, like, well, that's a little bit added. And then we have two crests on top. Well, that's a big jump right here, but not as big as having all three right here. And that's kind of what we do to create this KDF, or kernel density estimation. You also call this like KDE, right? So that's usually how you'll see it referenced. And usually this is really common for most of the stuff we do. Basically, we create this nice smooth function by taking each data point and creating a little normal curve, and then just add up all those normal curves together to make one big continuous curve. And you can see the advantage of this right here is that originally we had nothing in here, right? There are no points that happen. But by having this KDE, we now can say, well, there is some probability that something will land here. It's not like there's no probability, it's just that we didn't happen to see a point there, or maybe there weren't that many points. So the point is that we can see, okay, there's a probability of going over here. And this allows us to extrapolate beyond our data ourselves. And this tends to fit pretty well with how we actually approach the real world. All right, so any questions on how I form this kernel density function? Okay, cool. So again, the main thing, just think of those little tiny points. We basically write those little Gaussians. You can almost imagine we're smearing out that point across the x-axis to add them up. And then we add them all up together, kind of like you would do like with waves in physics or something. Okay. So,
I have a quick question.
Yeah.
Would you say if you had like many data points, would you say the KDF or E would approximate the bell shape?
It depends on the distribution. So it turns out if your data, which this tends to happen with our central limit theorem, we'll see later on, these things tend to form bell curves. But if your data was normally distributed, meaning that you have all these points and they tend to be very concentrated in one area and then kind of fade on the end, your KDE would approach a bell curve. Okay. So we'll actually see that, I believe,
if it's a normal distribution, the data.
Yeah. So that's actually what we're close to right now. So you can see this, for example, these points, this histogram, right? These are kind of like the number of points. You can imagine a bunch of points, kind of like how we had more than one point in this is bin together. We have a bunch of points that are kind of around here. And you can see here is this green, which is our parametric fit, which is really just saying the bell curve. We basically created an equation for the bell curve, the Gaussian. And that's what that green is. We say, all right, this looks normally distributed. It looks like a bell curve. We're going to say it's a bell curve. And we make the equation for it. And you can see it doesn't quite have this part, right? You can see it's close, but that's not exactly how the data actually are. So the kernel density estimation, though, we do all these little tiny like bell curves essentially for each of the data points, and we put those together, and it actually fits a lot of this extra little nuance. You can see here, it realizes, oh wait, like it doesn't all of a sudden spike up in the middle. It kind of flattens out in this middle part. And so you can imagine, though, if we had more data, maybe this data really should be normally distributed. And if we just had more data points, we'd actually find there's a bigger spike. Then we would see this kernel density estimation actually go closer to a bell curve. So this kind of allows us to, there's kind of pluses and minuses. The plus about the parametric fit is that we have it's a really nice equation. We love the bell curve. The bell curve is so nice to do math with. The parametric fit, there isn't a direct function that we pull from. We're basically creating a function from a bunch of bell curves because we love bell curves, right? We love Gaussian distributions. So the kernel density function is a little more clunky, but it allows for more of the organic shape and like distribution of an actual data set. So there's some drawbacks from both of them, and there's some advantages from both of them. Okay, so all right, so that's our parametric fit versus our kernel density estimation. All right, basically making a PDF. All right, so I kind of skipped over this part. So at this point, you might say, well, how do I make a parametric fit for like a Gaussian? And so we call it normal distribution. And that's what I'm going to show you from here, is that you'll hear normal distribution, bell curve, Gaussian distribution. All of these things are basically the same thing. There's a slight subtleness. It's not quite the same thing. A Gaussian versus a normal curve. A normal is basically reduced, so it's always equal to 1. Gaussian doesn't necessarily have to be that, but we usually use them interchangeably because they're basically the same shape. They're just scaled differently. So basically, the way you form a Gaussian curve is essentially this right here. You say y equals, and then a whole bunch of stuff, and you say, whoa, there's a bunch of little symbols and everything going on here. The main thing is that the x, basically say for each x, you put it in there, and that would tell you how high up on the y. And that will basically form your nice little bell curve or Gaussian. And the sigma right here, that's what that circle with little hat, like little, I don't know, ball cut kind of thing. But basically these are all numbers. So we have the sigma, which is our standard deviation. It's just a number. Our 2 pi, well, pi is just a number. E is actually Euler's number. So you can see 2.718, right? It's kind of like how pi is. It's irrational, kind of continues on forever. And then raised to the power of this negative x, quantity x minus mu, which ends up being our mean, another number, squared, divided by 2 sigma squared, which is our standard deviation squared. So you can see here is that basically what we do, we say, all right, here's our data. We try to form an equation that fits on our data really well. And then once we have this, like, okay, this equation fits really well on our data, we can say, well, okay, that means that's the standard deviation is sigma, and the mu of that data is the mean. So this kind of allows us to kind of work backwards. So you can kind of think of saying, we take our data, we say, all right, we're going to try to fit a Gaussian distribution on top of this. We kind of adjust the parameters until basically the Gaussian fits just about right. And then once we fit it just about right, then we say, okay, cool. Now that we have it fit, what is the standard deviation from that? What's the sigma from there? So you can basically pull those parts off. You could also do the reverse part, which is you literally say, what's the standard deviation of this data set? What's the average of this data set? And that will create your, what's it called? Your Gaussian distribution. So just like I did before, if you never look at the histogram, you can calculate the mean, you can calculate the standard deviation, by itself, and you take those values and you can just plug it into your Gaussian and you can create your Gaussian now. So, and that will make this nice fit. So it makes it really quick and easy to create. So that's why we like Gaussian. And it's nice because you can also do, it might not look pretty, but you can do some nice math like integrals and stuff like this on top of it that are really well known. So it means that calculation is really easy to do. Okay, any questions on like how we're kind of connecting these with our data? Okay, cool. So again, because it has this nice math, this nice distribution, we can actually use this a few things, for example, like the 68, 95, 99 rule. And basically all that is saying that how much of the percentage of observations occur within this Gaussian distribution. So as long as it's normalized, so there's, it's the area sums up to 1, is that if I go 1 standard deviation out to the left, 1 standard deviation out to the right, I basically contain about 68% of all observations within those first within that first standard deviation, left and right. If I expand it out to say, instead of 1 on each side, you expand it 2 on the left, 2 on the right, we now get about 95% of the values within here. And then if I do 3 standard deviations, I get from there to there 97 or 99.7% of the observations. I can actually keep extending it out more and more standard deviations. At a certain point, it doesn't make much sense to be like 20 standard deviations off to the side because the value is so small, it's basically meaningless at that point. But just know technically you could keep doing that. The Gaussian never reaches 0. It reaches 0 at infinity. So kind of fun fact about this is that when we talk about, when we do like testing, for example, we talk about how many standard deviations you are. And so, for example, if you did like a test with like a medical drug and say, okay, did this do well on the patient? Did it help the patient become better? What's the likelihood? And say, well, we use something called like a z-score, which is literally just the standard deviations, okay? And so you can see here, z-scores basically is how many standard deviations you are from the mean. So z is equal to this x value, wherever you are on this x, minus the average, and then just you divide by the standard deviations. So if you're off by this much, by 1 standard deviation, x minus 1 standard deviation is sigma divided by sigma, just 1. So this z-score really is just telling you how many standard deviations are you off. And that makes it easy for us to be able to compare different distributions because they're all Gaussian. So we can compare multiple Gaussian distributions and say, well, this one, the value we were off by 2 standard deviations, but this one we were off by 1.7 standard deviations. And so this is really useful for like in science, for example, like when we talk about this for a medical field, usually to say like something's useful, a good medicine, we say 3 standard deviations means like, oh, basically if we go any further than that, it's just by pure chance. And so it likely means that it's not just chance, it's actually causing something to happen. And that basically, oh, this drug is safe to use. For particle physics, for example, it's a little bit different. And remember, the more standard deviations you're off by, the more certain you are that it's not pure chance because it's so unlikely. So does anyone know how many standard deviations you have to do for particle physics for them to say it's a good result, meaning like it's a new interesting result? You got to guess. Yeah, turns out to be 5 is to say, oh, it's a good result. It probably means something. 7 standard deviations mean that it's legitimate and it's fit for saying we have new physics. The Higgs boson particle that was discovered about almost 10 years now is about 7.1 standard deviations when they announced it. And if you think about that number, that's like basically the probability of that happening is like 0.000000001% of the time that would have happened. And it's really unlikely. So that's why we're able to say it. Versus in medicine, you really can't do those kind of things just because people are just people. They're random. There's a lot of different factors. So if you were trying to approve a drug with 5 standard deviations, no drugs would ever be deemed good enough to actually be used for the population. And that's why we actually use 3 standard deviations. It tends to be the standard. So kind of give you guys some background. It's all based on context. But I want to mention the z-score. I'm not going to go far into detail. I'm going to kind of jump ahead just for a second. Is that we use a z-score for a z-sample test or one sample z-test. This is in the curriculum. And this again is on the, I see you guys all squinting right now. So like this is all in the GitHub right now that I have put together. I'll send it to you guys right now since you guys are all squinting. I don't want you guys to freak out, but I'm gonna put it away in a second because I don't want you guys to be like, oh, what is that? But I did want to point out that another instructor, Jeff, has a walkthrough video. He does a really great job of showing how you use the one sample z-test, so I'd strongly recommend watching that. I think it's a really good one. But I'm gonna put this away again. Okay, just know that you use a z-score to do your z-tests, okay? And I wanted to show you guys an interactive example. I'm not gonna spend too much time on this because I'm gonna move on, but it's a cool example to kind of check out. It allows you to do an interactive Gaussian. So you can see here, I can actually adjust the average, okay? And ignore this green part for now. But you can see I can adjust the average. So we can adjust that mu, and that's directly from this equation. So you see this equation? I'm basically just adjusting my mu, my average. And you can see the average just follows where that peak is. You can see, oh, at 2 is my average. And the standard deviation is basically how many, if I have a very large standard deviation, it basically means I have to go really far out in order to capture 68% of all the values. So if I make this bigger, you'll see my my Gaussian get much smaller, very, very fat. Basically because I have to expand really far out to include everything that's 68%. Versus if I make it really small, it's gonna make much more of a peak because now it's like, oh, I only need to go this far to get 68%. So basically that adds this part up here. So you can kind of play around with this guy. And then this right here, just to kind of show you guys, is that this represents, let's see here. You can see, where is it showing up? No, it doesn't show that. No. I'm trying to remember where this comes out. Basically, this is showing what percentage is being covered over. So you can see like that would be your percentage of, oh, probability. That's probably what we're doing. Yeah, 68%. So you can see about 1 standard deviation is about 68%. If I were to expand it out, so, or let's say let's say expand it out, you can see, oh, it only covers about 34%. If I make it so, let's say that's about 2. So if I make it about halfway here, this would be about 95%. So when you go 2 standard deviations out, I now have 95%. So kind of a fun thing to play around with. If I wanted to show you all the different standard deviations, so you can see here, if I expand this out, this is 1 standard deviation away, 2 standard deviations away, 3 and such. And you can see 5, I don't even know where 5 is because it's so hard to like tell from here. It's barely anything. So just know that's kind of like how you can form this. So a good thing to play around with. But but I included there. Okay. So that's our normal distribution. Any questions on normal distributions, Gaussians, all that stuff?
I've got a question.
Yeah.
So you talked about medical research.
Mm-hmm.
Don't they use something called a p-value? Is that?
Yes. Yes, and we'll actually talk about that too. I believe.
Later on.
Yes, we'll talk about that. P-value.
Oh, okay.
We will talk about that, and it's related to partly with the standard deviation, but also a little bit. It's a little subtle, but
it's like a 95% confidence or something, right?
Yeah, it basically tells you how confident you are based on your data and based on what's it called? Basically how many standard deviations. And so they're related. I don't want to say they're interchangeable because they're not, but they're related to each other. So if you increase the standard deviation, you would expect a change in the p-value and stuff like that. But they're describing more specific comparison, and that's where the z-test really comes in. But yeah, good call. Okay. And we'll talk about this definitely for next time if I don't get to all of it right now. But all right, so I did want to talk about deviations from the normal distribution. This would be pretty quick. So this thing, usually we'll talk about skewness. So if you remember our standard deviation, I don't know if you guys recall this, but when we calculated standard deviation, it was something along the like x minus mu squared. Does that kind of remind you? And then we sum up all of those different changes. Does that seem to ring a bell a little bit? So x minus mu squared. So basically that standard deviation, and this is about sigma. Well, this is technically the variance, but like you can think variance, standard deviation, they're related. That sigma, that variance basically tells you how far that is, how the points are spread out. Our skewness is kind of like that. Our skewness is kind of like saying, how does the value spread out from each other? So the curriculum kind of gives these equations. You normally don't have to know these equations, but main thing is to know that our skewness basically tells us like, well, there tends to be more of a bias towards one direction versus the other. So this is a nice symmetric distribution where the mean and the median are both in the center. In this case, the mode too. Well, we don't have to talk about that. But the main thing is the mean and the median is that are centered. If you have a more skewness, for example, positive skew, okay, when it's skewed off to one side, basically it means that that median is what's called, it's more robust, if this makes sense. So it doesn't fluctuate as much, but the mean is really influenced by these, what we call like outliers. As it gets pulled off the side, the mean kind of travels along with it. So you can see here is that the median's pretty close to the top here. So if I imagine I kind of take this thing and squish it down, our median will stay like, you know, smooth a little bit, but our mean will move a lot more. And that's why this part goes here. So that's kind of like something you keep in mind with your skewness. So it's never enough just to do the mean or, you know, average. You have to kind of consider like, well, what if there are values that are pulling off? And this is why we talk about like outliers. Outliers can be a huge deal for the mean because it's just not as robust. It can get influenced very easily with averages. That's why a lot of times we'll quote the median as well. And of course the mode is a nice thing to know where if there are frequent values that come through. Skewness, I'm sorry, that is skewness. And there are the equation that goes through it. I usually don't see skewness quoted in research in the sense like, oh, a skewness of 0.32 or something like that. You can technically, I've never really see that. Maybe I'm just not looking at the right research, but mostly skewness is more of a thing that you can quantify it, but it's arguable like how do you quantify it? That's what someone asked before. And kurtosis, which again, you can quantify it, but again, almost, I don't know anyone who actually quantifies it. Oh, I forgot to say, sorry. You can quantify it, but there's kind of argues like, well, how do you quantify it exactly? This tends to be skewness, tends to be something to the power, like we saw with variance, sigma squared is variance. Sorry, I'm not good at drawing. Is something like x minus mu squared. Skewness tends to be something along lines up to the power of 3. And then kurtosis ends up, for quantifying, ends up being something along the lines of the power of 4. Again, these are just all kind of just ways to summarize it, but that kurtosis, all that basically describes is essentially like, see how like peaky we are. Like this would have a high kurtosis versus something that has a more moderate curve like this. This would be our different kurtosis. And basically it's kind of like saying like, well, are the values tend to be more squished together into this one direction? And that's where we can have this kurtosis. And again, the curriculum goes into more detail, but I think they're more important to know that they exist and that your distributions can deviate from it. not so much in the sense of like, how do you exactly quantify it? Because the quantification, basically, it's just a summary of what your data actually represent. So just kind of be aware of those two things. Any questions on any of those, skewness or kurtosis? Okay. Skewness you'll see more commonly. Kurtosis does come up time to time, but usually it's not as important just because it's a higher order function. Okay. And I want to make sure I had enough time. Okay, so that is our normal distribution. And then this will lead us into statistical testing. So next time, we'll actually talk about linear regression. And that will lead us into multiple linear regression. And that will allow us to do a bunch of different things. But yeah, we have enough time, so I want to make sure we do this. So for statistical testing, I mentioned about the z-test. And so I don't know why this got all funky. Okay, there we go. This x bar. So just know that we have something called the sample and the population. The population is kind of like the true values that we see. And our sample is kind of like we take some portion of the population. So our mu usually represents the actual population mean. And that might not always be known. Just know that that's what we talk about when we say mu. We really mean the population, the full population, not your specific experiment. In your sample here, usually we tell you as x bar. Okay. We also use in standard deviation, we tend to use this sigma to say that it is the population standard deviation, how the population varies. And then we might use the letter s, like a lowercase s, to say it's our sample standard deviation. Okay. So just know that we have our z-score here, and this z-score basically represents for a population, saying, all right, taking the population mean, I'm sorry, not population, the sample, taking the sample mean minus the population mean, divided by basically the sigma here, divided by square root of n. This allows us to basically define and compare, is our sample similar to our population? So for example, if you were to do a survey with a bunch of second graders, you know, about who's their favorite superhero, or who do they favor more, Batman or Superman, something like that, right? And you then ask the whole population for it. Well, you want to know, well, was me asking just my second graders, is that a good example of the full population? And you probably intuitively know that's probably not true. But this way it allows you to actually test this part out and say, how far away is our sample from the true population? And this is what this kind of allows us to say, is our sample that we're talking about match with the rest of the population? This is also like when you talk about statistical testing, where you have, say, oh, we tried a new treatment, and we want to see, did our treatment group actually differ from our control group where we didn't give a drug to? And so this is saying, oh, well, our treatment group is kind of, in a sense, our population, saying this is what the normal population would kind of be distributed with. Some people get better right away without any help. Some people never get better without any help. And you want to say, well, if I give a treatment, does it actually help? And you want to compare those things. And that's where our statistical significance, our z-score, comes in. Okay. So again, this is where we kind of use comparison. And again, I'm going to point you back down to Jeff's walkthrough. He does a good job showing this. I think he does it with hockey players. Say, like, is the hockey team significantly better than the rest of in the league, or are they just an average team? It's just hard to tell. Okay. So this.
What's n there is the size of the sample?
I'm sorry, what was that?
The n letter.
Oh, the letter n is, yes, the size of the sample. Okay. Yeah. So basically, it's like if you have many more people in your sample, or many more subjects, or whatever you're doing in your sample, it doesn't have to be people, it could be other things, right? But if you have more data points in that sample, basically then you know that you're probably getting closer and closer to the population. And so that way it has smaller and smaller effect in that sense. So you can kind of see, like, if I have a big N, this will make sigma smaller, make this sigma smaller, and this basically makes this z-score kind of go up. So you can have more and more significance. Basically, it's a kind of a factor to make sure that if you have more people in there, you can trust your z-score. If it's really close, it's probably really close. If it's really far away, that means it really should be far away, because it's a lot of people you tested out with. Okay, good questions. All right, so this couple things, yeah, I'll say this, couple things. So this will lead us into hypothesis testing. We'll talk about this more, especially in module 2, but I want to introduce it now, is hypothesis testing, which is kind of like what I described. And again, point down to Jeff's video, good one. We talked about the null hypothesis and the alternative hypothesis. So the null hypothesis is kind of like what I said, like that control group. Basically, it's like it assumes that nothing new has changed. It seems like basically you had no effect. That's kind of what the null hypothesis is. Like, oh, there's no change. And then alternative hypothesis is basically the thing that you're testing out, your sample has an effect, or that your sample is significantly different. You're statistically significant from the average, from the population. Okay, so note that there's this null hypothesis versus alternative hypothesis. And again, note that I'm going to talk about this again in module 2 when we get closer to it. But one thing I did want to emphasize is that I think the curriculum, it kind of rubs me the wrong way. I don't like this phrasing. You should always be trying to reject the null hypothesis. You never accept the alternative hypothesis. So what you're trying to do is basically you're trying to disprove your own treatment. So like if you're trying to test out a new drug, your alternative hypothesis would say, oh, the drug has an effect. The drug makes people better. My null hypothesis says the drug has no effect. And so your attempt to basically reject is basically say, I want to get rid of and I want to prove that this null hypothesis, that this drug has no effect, is wrong. That's what you're trying to reject. So essentially you have two options. You either reject the null hypothesis, which basically you accept your alternative saying, oh, my drug does have effect, or you fail to reject your null hypothesis. You never like in that sense, like accept it, but you fail to reject your null hypothesis because maybe it's just like by chance you just didn't have enough participants and you just didn't have enough data, and so you fail to reject it, but maybe it is true. So I just wanted to add that kind of terminology for you guys. So I do know I'm a little over, but I kind of wanted to show you guys this one last part. Just know that this hypothesis is based around the normal curve. So basically these different tails end up being like, for example, this alternative basically comes in 3 different forms. It's either the average is for our population, this really shouldn't be mu, but the average is greater than our value, which means we're in this tail end over here. This is why I was talking about the 3 standard deviations versus like, 5 standard deviations for physics or something like that. Saying like, is it significantly bigger? Is it significantly smaller? Or is it just different? So you can see like, if it's different, we're saying there's no difference in the mean right here. So we're basically either too small or too big. So these are your kind of 3 different alternative hypotheses. Okay. And then, yeah. All right. If you guys are cool with me going a little bit over, I know it's just a minute over. Last thing is our p-value, which is super important. And again, I'll talk about this again in mod 2. But our p-value basically allows us to say how significant something is. So I'm going to point you guys to this video right here, this p-value puppies, which is just like the perfect kind of video. It explains p-values using puppies, which is awesome. But basically the idea here is that your p-value tells you kind of like, quote unquote, how weird your sample is. It's like, is your sample different from like all the possible things? So in this video, they kind of compare if you come home and you see your little pupper like got the trash can over its head, and it's like, well, what's most likely? It's like, well, it's possible maybe your neighbor broke in and like trashed the place and put the trash on top of your puppy's head and then ran out the door before you came home. That's possible, but it's unlikely. And that's kind of what the p-value kind of tells you. It's like, this p-value tells you how likely is it that you would have observed this kind of thing. And this translates into confidence values. Again, I didn't go into full detail here. We'll talk about this more in mod 2, but there is in the curriculum right now. Basically tells us how significant is our value. Now, I kind of want to give a warning here, is something called p-hacking, which I think Andrew had just mentioned, p-hacking. And p-hacking, because p-value is the thing that we usually quote. We say, oh, we have a 95% confidence interval, or we're 97% confident that our value is within this range or whatever. And so p-hacking basically is you keep testing things over and over again. Well, one way we can do it is if we can test things over and over again to make it our p-value more significant, or basically we get more confidence. We adjust our p-value by testing things over and over again. So usually our p-value, depending what you have, your confidence interval, you kind of set a certain threshold. And so usually it's like 0.05. So a smaller p-value basically is a good thing. It's like, oh, it means it's statistically significant. So usually 0.05, this is from XKCD, but basically this is usually what we want. We want a value that's lower than 0.05 for our p-value. So usually, oh, significant. But if you had it exactly 0.05, it's like, ooh, like maybe retest it. And these are the kind of things that kind of come up again and again. Sometimes the threshold's smaller. This is a joke. just to make this clear. This is not something that's actually something you have to remember or something like that. There's kind of some extra stuff like, well, what if you just keep testing over and over? So there's this one scenario which I just love. This is, again, same comic, is that the p-value really comes down to the fact that it's telling you, if you were to repeat the experiment again and again, how many times would you expect this value to occur? And so the problem is that if you test the same experiment over and over again, it's kind of like flipping a coin. It's like if you flip a coin, like let's say you flip 5 times, and you flip the coin 5 times, and you'd expect half the time heads, half the time tails, but sometimes you might get all heads, right? And if you kept doing this, how many times would you have to flip it to get all heads? Well, that's kind of like what the p-value is saying. So the problem is like if you try testing out each part. So this one right here basically says, oh, someone comes in, jelly beans cause acne, right? So they investigate, right? And basically they're saying, okay, we need a p-value that is less than 0.05. Basically, that's the standard, saying, okay, we need to say, is it statistically significant? And so they test it out and say, oh, okay, the p-value is higher than 0.05. Said and done, right? Our experiment is as well. It's like, well, I think there's a certain color. So then they do the whole test again, but they do the test for every color. So the problem is now now they're doing multiple tests. And in this case, actually, again, xkcd.com is really great at doing these little like kind of mathy, sciencey kind of comics, which really, like, they're so relevant to what we do. But they end up doing 20, or yeah, is that 20? Yeah, 20 different experiments, which 1 out of 20 times, you might get a p-value slightly higher than 0.05, which in this case they find actually with this green jelly bean right here. They say, oh, it's a p-value less than 0.05. So this is actually a real thing that happens. Is basically there's one experiment that was interesting. The scientists said ahead of time, said, I'm going to legitimately do science. I'm going to do p-hacking essentially. I'm going to publish it, and they're going to publish my paper, and everyone in the media is going to take this over, like going to take hold of this because they hear this significant value from the published paper. He basically tested a bunch of different little things to see if something would change in their weight, change in their like mood and all these things. And basically he found one thing out of all the things he tested that was a significant p-value, but it's because he tested so many things. And that significant thing was like, oh, there was a slight weight reduction by having dark chocolate. And so this was repeated over and over in the news, saying eating dark chocolate can help you lose weight. And in fact, you might have even heard this thing. You might have heard people say, oh, I hear dark chocolate is supposed to help you lose weight. And it actually comes down to this study that literally the person said, I'm going to make a study that has legitimate science, but it does p-hacking, and it's going to take it, and people are going to believe that it's true, like in the sense that scientifically true. And that's exactly what happened. So just kind of know is that like these things can kind of happen in the sense that like you have to be really careful as a data scientist because you have a lot of power of like how much data you have in what you can do. And also not just for what you can lead the rest of the public to say, but also yourself. Like if you're trying to do a study and you find that these p-values and you're statistically significant, you come across these things, you might try to convince yourself by just repeating this stuff over and over again, and you realize you're actually doing this thing. You're like, oh, I'm overfitting. So I kind of wanted to throw that in there, but we'll revisit this again in the future. But I just wanted to throw this out to give you guys. And plus, it's a funny comic, I think. Well, I think it's funny. I don't know. All right, everyone. So I'll go ahead and stop here unless you guys have any quick questions.